right, everyone, we are hopefully ready to start into chapter 21. Okay, let's quiet down. This is, I guess, our third chapter now of carbonyl chemistry. And I think, as far as I was looking ahead, we got 2 more chapters of carbonyl chemistry as well. So we have, I think it's chapters 21 and 22 to do the end of this week, and then after the break, and I believe that our next exam, if you actually want to think about that, and that far ahead, is on April 1st. Yeah. All right, so this chapter, what it does, I've mentioned this a couple of times, is it focuses more, okay, let's quiet down, please, on aldehydes and ketones. We've already looked at some reactions of aldehydes and ketones. We've focused on the reactions with strong nucleophiles. We're going to do more nucleophilic additions in this chapter, but we're going to use some weaker nucleophiles. We're also going to touch on the naming, some physical properties. We're going to review how to prepare aldehydes, and then we'll get into some reactions. All right? Oh, damn. Oh well, we won't do the clicker, I guess. Too busy talking. Speaking of aldehydes and ketones, follows the same kind of rules we've been doing up to now. Where's my other notes? Oh, yeah. When we do aldehydes, what we do is, like always, is we start with the longest chain that includes the aldehyde, all right? That'll be the alkane, the parent name. What we do is we drop the E on the end. We add Al for aldehyde. Okay, so we go to a generic name of alkanal. All right, so if we do a simple aldehyde like the first one there, we find the longest chain. It has to include the aldehyde, and the aldehyde will always be number 1, so we don't have to give a number for it. And so we're just going to number this 1, 2, 3, 4, 5. Right, we have a methyl group at position 2. So we have 2 methyl pentanal. Okay? If the aldehyde is attached to a ring that would be kind of the parent alkane, what we do, remember with carboxylic acids, we had the name, like if this was a carboxylic acid, we'd say cyclopentane carboxylic acid. Here, what we do is we add carbaldehyde on the end. So this would be a pentane. Oh, this thing is it doing that up there too? Pentane carbaldehyde, right? And then we have an ethyl group attached to the ring. We just now number from the position where the aldehyde is attached to the ring. So 1, 2, 3, it would be 3 methyl pentane carbaldehyde. Ethyl, correct. Just checking to see if you're awake. One person was awake. All right. Sometimes we're going to have more than one functional group, and in this case we have an alkene and the aldehyde, and so we can just put both of those in the ending. Instead of, like that first one, pentanal, we just put an "ene" in there, pentanal. Or in this case, if we number this, we're always going to, again, start with the aldehyde, 1, 2, 3. Dang. Counting, I guess, wasn't my best subject. 4. So this is a butenal. So we're going to write this bute, and then we're going to put the number for that double bond, 2-enal. We have, again, a methyl group, this time at position 3. So 3-methyl butene, but-2-enal. Not very smooth named, say. All right, so that's how we do aldehydes. Ketones, what we do is we drop the E again, and we add -one. So we have alkanone. All right. So then, if we're going to do these, we're going to number, though, to give the ketone the lowest possible number. So again, the longest chain has to include the functional group here. So this would just be 2. We got to put a number. I think they put it out in front this time. Hexanone. You know, it could probably be hexane 2-one as well. Okay. If it's in a ring, we don't have to do anything fancy. We just use the same ending. This is cyclohexane, so cyclohexanone. All right, because that would take number 1, we don't have to give it a number, but we're going to number this then to give the substituent the lowest number, so 2-methylcyclohexanone. If we have a double bond in the structure, we do the same as we did above. The ketone takes priority, so it gets the lower number. So if we numbered this from left to right, the ketone would be at 4. Even though the double bond would only be at 2, we're going to number it from right to left because that puts the ketone at 3. So we're going to number it this way. So this would be a hexenone. So it is going to be hex 4-en. Oh, we got a given position for the ketone this time, though. 3-one. Anything else we should put on this one? Yeah, so we have to say something about what the geometry of the double bond is. So because there's only 2 substituents on that double bond, we could use trans. Right? Or we could say, what else could we do? E. Okay? All right. So there are some of them are good to know. Some of the small aldehydes or ketones, or some of the common ones at least. So who knows what the first one in the upper left is? Formaldehyde. Right, so if you've ever done, say, dissections in the biology lab or something like that, you know, formaldehyde is used as a preserving agent for things like that. The next one, so what would be the IUPAC name of formaldehyde? Methanal. Because it'd be methane, methanal. Right, so that would be IUPAC. Nobody usually calls it that, though. Formaldehyde is pretty accepted. The next one with 2 carbons is usually just referred to as acetaldehyde. Acetaldehyde, that one's kind of fun to say. Or ethanol. What's the next one? We already talked about that one. Benzaldehyde, good. All right, there's some common ketones as well. What's that first ketone? Acetone. It's a common solvent. The next one, it essentially has this kind of acetyl group. So wherever you see this acid, this part comes from acetic acid, right? So it's the 2-carbon piece. So that's the common part. So this is called acetophenone. And the next one is benzophenone. So benzophenone has a kind of an interesting application in the chemistry lab. So like we've been talking about, when we run reactions like organolithiums or Grignards, we have to have a solvent that is extremely dry. All right, so we want to make sure that it has no moisture at all, and so we have to usually distill it from some drying reagent. All right, and I think that this is not always considered the safest way to do this anymore. They don't always use this, so let me try my artistic talents up here. So there's an apparatus like this, so you can have a big, that's probably not even big enough. Like, if you use this very often, you know, maybe a 2-liter flask or something, you put your solvent in here. Maybe the common one to use this benzophenone is if you were going to use THF. If you use it routinely, then you want to be able to distill this easily, and if you can distill it immediately before you use it, then it's going to be the driest as well. So then you have an apparatus that goes up like this, and it has usually a valve on here, and it'll have a big bowl, not that big. My artistic talents aren't that good. A big kind of a bowl here that has a thing that goes up like this, and it has a hole in here. That's the top here. And then usually, let me think about this. It has to have some kind of a valve here. And then we put a condenser up here. Water condenser. Okay? Oh, and so then we have to have usually a port up here, stopcock, and a little port like this. Okay, so the way that this works is down here in the bottom you have to put some kind of drying reagent. So what we used to always do, and I probably do this sometimes, is we put like some chunks of potassium metal in there, which is super reactive. You know, it'll definitely catch fire if you add it to water. And then you add some benzophenone to it. Okay? The benzophenone reacts with potassium. This won't be on the test or anything. I'm just stalling and just talking. And it forms something that we could maybe draw out like this. We're going to add an extra electron here. So it forms like a radical anion. I'm not sure if that's exactly right. Let me think about this. So it and then the other thing you get is like potassium plus. I don't know if I do this quite right. But this stuff is blue. All right? You can only form this in the absence of water or oxygen. Okay, so you boil your THF with potassium, and that reacts with any water in there, right, forming potassium hydroxide. And if this is dry enough and no oxygen, then potassium can give its electron to benzophenone, and the solution turns blue. And so that's proof that this THF is ultimately dry and free of even oxygen. Okay? So if you're still, call this a, still, and as long as it's blue, you're in good shape. Okay, so if you want some, if you're going to do a reaction, turn up temperature, close this stopcock over here, and it distills up like this, goes through the hole, comes up here, and it drips down into here, and it fills up this bulb with THF. Okay, so it just stops there, and if you forgot about it, it would drain down. It wouldn't like fill up the top or something like that. And then you take like a syringe, a needle, and you'll draw out, THF out of the bulb right here. Okay, and then you can take it to your flask and use it directly, so you know that solvent is super dry. And then when you're done, you just open this stopcock, drain it all back into the bottom, and then you just store it like that until you need it the next day or whenever you need it. All right? They have a little diagram in the book, but I thought I could do better. All right, so that's just a little side thing, just a little special interest story. Probably have a question on the exam, have you draw that. See if you can do better than I did. All right, so benzophenone, there is a way to just, common names of ketones. I won't ask you to do this, but just so you know, right? So the common way is usually just to name the two alkyl groups and then say ketone. Okay, so this would just be ethyl, methyl, ketone. Okay, so this is a common way. Physical properties. I just took this one straight out of the book. If we compare boiling points and melting points to some of the functional groups that we already know, we know that alkanes have very low melting points and boiling points, right? Because they have very weak intermolecular forces. All they can really have is van der Waals interactions, which are just these transient dipoles. Okay, so those are very weak, so they have very low boiling points and melting points. Much higher is over here with the alcohols, because of course they can have, this is for van der Waals, they can also have dipole-dipole interactions, and then they can have an especially important type of dipole-dipole interaction, and that's the hydrogen bonds. Okay, so they have quite high boiling points. The ketones and the aldehydes fall kind of in the middle, all right, because they can have van der Waals, they can have dipole-dipole interactions because we have this polar carbon-oxygen bond, so the partial negative on the oxygen can align itself with the partial plus of another molecule of the carbonyl carbon, but they can't have any hydrogen bonds. Okay, so they're kind of in the middle. If we have any aldehydes and ketones, they will always, it's kind of small probably, but they will all dissolve in organic solvents. If we have, says less than or equal to 5 carbons per carbonyl group, then they can dissolve in water. So say acetone readily dissolves in water. Okay, but if the alkyl groups get longer than 5 per carbonyl group, then it's that hydrophobic part that dominates its physical properties, and then it won't dissolve in water anymore. It will only go in the organic phase. Okay? Same kind of trends we've seen before. The other thing about the physical properties are the spectroscopy. So I just want to throw up a slide now and then on this to remind you that we're still thinking about this stuff. So for aldehydes especially, we haven't really talked about this. Of course, for aldehydes, we have the carbonyl stretch. But the other thing that's very characteristic is that the carbon-hydrogen of the aldehyde, so this bond right here, has a very unique set of peaks. And those are right here. So it's these two peaks. And they're kind of on the short wave number side of the normal sp3 hybridized carbon hydrogen stretches. Okay, so they kind of are right off of that side on the low side. Always a pair of peaks. All right, as far as NMR goes, we can easily see aldehydes in the proton NMR spectrum. They're usually out in the 9 to low 10 range. If, like in this case, they have hydrogens on the adjacent carbon, they can couple with those protons, right? So here, if you can see that, it's kind of a small coupling, but that looks kind of like a triplet. And that's because there's a CH2 group on the adjacent carbon. If we had that aldehyde and there was only a CH next to it, then it would be a doublet. If we looked at just the spectrum of benzaldehyde, what would that proton look like? You guys remember the structure of benzaldehyde? Yeah, the benzene ring. Is there going to be any splitting on that proton? No, there's no protons on the adjacent carbon, so that would be a singlet. So it tells us what the coupling is on the adjacent carbon. In the in the C13 NMR, we talked some about this. We can pick out the carbonyl carbons very easily. Aldehydes and ketones are usually 190 and above. And so, especially if we have a proton NMR and a C13, or even a C13 and an IR, any of these two combinations, we can easily pick out an aldehyde. Okay? I threw in one extra one here. All right, so this is IR and proton NMR for a molecule that has a molecular formula of C9H10O. So take a moment and see if you can figure out what that is. Gives you what the integrations, there's two of those peaks that are expanded too. So this goes to that side and that one goes to the other side. All right, so how many unsaturations do we have? 4 or 5? 5. 5 unsaturations. Do we have a benzene ring? Sure looks like it, right? So we have these protons here, just above 7, which is in the benzene ring. Benzene range, we have 5 of those, right? So that suggests we have a mono-substituted benzene ring. Okay. Do we have an aldehyde or a ketone? An aldehyde, right? Because, well, what pieces of data here tell us we have an aldehyde? Right? These two peaks right here are for the aldehyde proton. Here's the carbonyl stretch. What else tells us we have an aldehyde? Right, the proton NMR, right? This goes to that proton right there. They haven't expanded it, so we don't really know what kind of splitting it has, or if it has any. All right, what else do we have here? Or what's the rest? So we have an aldehyde. Right, what do we have left that we have to put in there? 2 carbons, and we have 6 hydrogens so far, 2 carbons and 4 hydrogens, right? So how do we put the rest of it together? Yeah, so we're just going to put a CH2 group, a CH2 group, and we're going to attach that to our aldehyde. I don't know why that thing keeps refocusing all the time. All right, so notice we know that those 2 CH2 groups are next to each other, right? Because the 2 protons at around signals around 3 are both triplets. Right? So each one is getting split by the adjacent CH2 group. Right. Any questions? Okay. So now this is review, and this is a way to organize some of your reactions. So we're just going to review, since we're going to do aldehydes, how can we make an aldehyde? Okay, so if we want to make this aldehyde, what other molecules can we convert to this in one reaction step? Right? What functional groups can we convert to this aldehyde? Yeah?
Primary alcohol.
Primary alcohol, good. Right, so we could make that from this alcohol. What would we use to do that? PCC. PDC is another one, but I don't think they usually use that in here. But pyridinium chlorochromate. Pyridinium dichromate is another reagent, but I haven't ever seen it in these books. All right, what's another functional group that we can convert to an aldehyde? An alkyne. So how many carbons should be on the alkyne total? Right, because we have to lose a carbon when we convert. Well, no, that's not right, is it? So what kind of reaction are we going to use here? Well, if we do an ozonolysis of an alkyne, what kind of a functional group do we get? A carboxylic acid. So, in fact, we could do that, but then we'd have to reduce the carboxylic acid all the way to the alcohol, lithium aluminum hydride, and then we could oxidize it to the alcohol. Okay, so we could do that in 2 steps, but how can we convert that alkyne? And we'd need 1 more carbon on this carbon chain, right? Because an ozonolysis is going to carve off 1 carbon as well. Right, so it's a hydroboration oxidation. Okay, so usually they do this one with this borane that has 2 different alkyl groups instead of just borane, and then hydrogen peroxide and hydroxide. All right, so remember this is a net hydration reaction, so it adds an H and an OH, the OH going to the less substituted side to form an enol, the enol tautomerizes to give the aldehyde. Okay, what else can we convert into this aldehyde? Yeah, it'd be 2 steps. What can we do directly in a similar way? Acid chloride we can do, right? And to do that, we need this kind of specialized reagent that has these 3 tert butoxy groups on it. Lithium tri-tert butoxy. No, it's lithium tri-tert butoxy aluminum hydride, 2H2O. All right, anything else that we can reduce to an aldehyde? What about an ester? Okay, remember we can do that in 1 step from that reagent called dibal. Diisobutyl aluminum hydride. Any other ways? I got 1 more on my list. A what? An alkene. That is correct. Okay, so how can we, is that 1, 2, 3, 4, 1, 2, 3, 4, 5. How can we convert that alkene into the aldehyde? So this is the ozonolysis reaction. Ozonolysis, and then remember that you have to work that up with either dimethyl sulfide, or you can use zinc and water, I think. Right, so that's another oxidative cleavage. All right, so keep building these kind of things up as we add new reactions in. So ketone. So here's this acetophenone. So what could we convert into acetophenone? An acid chloride. Put that over here. And what would we use to convert the acid chloride into the ketone? An organocuprate. Exactly right. I put that in the wrong place, didn't I? Okay, so that's like lithium, copper with, remember we have 2 of the alkyl groups. So in this case, we want to have 2 methyl groups. So that would be 1, 2. We have to quench it with water. All right. What else? Huh? Friedel-Crafts acylation. Good. So then we just start with benzene, right? We use acetyl chloride and aluminum trichloride. Anything else?
Secondary alcohol?
We could definitely oxidize a secondary alcohol. Right, and here we could use PCC again, or we can use any of those chromium reagents as well. So say chromium, this isn't working that good, chromium trioxide and sulfuric acid. Anything else? An alkane? An alkene. And what reaction would we be using here? Are you just guessing?
Well, maybe.
Okay, if we put an alkene right here, where the ketone is, what kind of reaction could we use to convert that alkene to the ketone? Ozonolysis. All right, and we could also make this from the alkyne. Right, and this is just a hydration reaction. So we've got H2O, sulfuric acid, and sometimes on these they put in this mercuric acetate. It's a GSO4 as a catalyst. All right, so that as well as a hydration reaction, right? But this time, last time we used the hydroboration oxidation one, and it did an antimicrobial, put the OH on the end that gave us an aldehyde. In this case, it would follow a Markovnikov addition, right? So proton would go on the end, OH would go on the more substituted side to give an enol, and that enol would tautomerize to the ketone. Okay, so we got a bunch of ways to make aldehydes and ketones already. We hadn't even started this chapter yet. Okay, so what we're going to do now is we are going to look at a couple of general mechanisms. One is the mechanism we've already seen for addition reactions, and the other one is also going to be similar, but it's going to be with a weaker nucleophile. Okay, so we're going to look at some general mechanisms, and then we have this series of nucleophiles that we're going to look at. Okay, we're going to quickly review what we learned from the last chapter, strong nucleophiles, and then these other nucleophiles we're going to look at. Cyanide is a nucleophile. Nitrogen-based nucleophiles, amines, so primary and secondary amines, oxygen nucleophiles like water and alcohols, and then we have kind of an oddball reaction that's called the Wittig reaction. I'm doing these in a slightly different order than the book because I can't figure out why they did it in the order that they did it in. And I think this is a more logical way to do it. Okay? Put this and the next slide in the opposite order on yours. Okay, and I swapped it right before. Okay, so what we learned in the last chapter was that for both aldehydes and ketones, if we react them with strong nucleophiles, that nucleophile with its minus charge can attack the carbonyl carbon. So that's the delta plus end of the carbonyl, right? The oxygen, or the pi bond goes up on the oxygen, and we form a tetrahedral intermediate. Like this. Here's our this is supposed to be our nucleophile. And we have this R group, and that R group could be either a carbon if it's a ketone or an H if it's an aldehyde. All right, and then we were essentially done at this point, and so then we would add water to quench any excess nucleophile that we might have used. We always draw these reactions as a 1-to-1 ratio, but if you were doing it in the lab, you'd tend to maybe use 1.2 equivalents of nucleophiles just to make sure that you can drive that reaction all the way to completion. Okay, so we'd have to quench that, and we want to protonate that oxygen, and so we get this alcohol. Okay, so if we use a weaker nucleophile, and so here my nucleophile, it still has to have a pair of electrons on it, but that nucleophile may have a proton on it still. It may be neutral and not have a negative charge. So if this nucleophile is too weak, then it just won't react with carbonyl, right? And so if that's our situation, we have to do something to make the the carbonyl more reactive. And what we oftentimes do is we add a catalyst. And our catalyst in this case is going to be a proton. All right, so what happens, and I think I kind of alluded to this before, is that if we protonate the carbonyl oxygen, I'm going to draw it down this way. Then we get a species that looks like this, and we have a resonance structure that would put those electrons, the pi electrons, up on the oxygen and the plus on the carbonyl carbon. So what this shows us is by protonating the oxygen, we've increased the amount of delta plus on the carbonyl carbon. Okay, increased delta plus. Okay. And the more positively charged that carbonyl carbon is, the more electrophilic it is. And so now it can react with a much weaker nucleophile. Okay, so now this can react with, I'm not going to really draw out all the steps here. This is going to work kind of the same, but I'm not going to, there's going to be some acid-base chemistry steps, and I'm not going to draw those all in yet. Okay, so basically we just get our addition step like this. Okay, but what can happen after that is if we have acid, then if that OH protonates, it can be converted to a good leaving group. And if this nucleophile has non-bonding pairs of electrons, okay, what can happen? H plus, let's kind of draw this out. We form a water molecule here. And then those electrons on the nucleophile can push, come on, that's supposed to go onto the oxygen. This is not really working very fast today. And so what we end up with is something that looks like this, with our nucleophile and our R like this. And depending on the protons or not, this could have a plus charge up here, and in some cases it'll stop here, sometimes it'll react further. Okay, so we have a few extra steps that we can do sometimes when we use nucleophiles, especially like amines and alcohols. Okay? All right, so I think let's just stop there for today before we get into any of these reactions. We just don't have enough time. All right, so I will see you guys in the morning.